Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Today, let's talk about the last topic in Chapter 5, effusion and diffusion. Let me describe a scenario for you. If we have a balloon full of gas, and then we use a needle to poke on it, then the gas inside of this balloon will escape through that small hole, right? So that's exactly what effusion is. The effusion refers to the process by which a gas escapes through a tiny hole in its container into an evacuated space. Okay, for effusion, you need to know a law, that is Graham's law of effusion. That Graham's law of effusion says the rate of effusion of a gas, how fast the gas moves through this hole, is inversely proportional to the square root of its molar mass. You can see the mass equation here. Rate of effusion is inversely proportional to the square root of this molar mass. In the textbook, you probably also read the equation 5.14. It says rate A over rate B of effusion, that is two different molecules, A and B, that equals to the root mean square speed of A versus or over the root mean square speed of B. And then plug in the number of the average kinetic energy, we can have this equation. And finally, the last step, it's wrong. Okay, last step, rate A over rate B should equal to the square root of molecular mass of B over molecular mass of A. Okay, what's written in the textbook was wrong. It gives you another square root. Okay, so that means if we have a heavier gas, if B is heavier than A, then the rate of B is smaller than A. Okay, it's inverse. So under the same circumstance, if we switch to a gas with a larger molar mass, we will have the smaller rate of effusion, and we can slow down the effusion. Okay. Another concept that is very similar to effusion is called diffusion. Okay. Diffusion is the movement of one gas or fluid through another. So in this schematic, we have a long tube of container, and we have a lot of gas inside. If you follow the track of this red lines, that shows how this particle moves along its way from left to right. So the way that this gas moves, it's all hit by other probably gases and try to make it away from the left to right. And this may not be straight lines. Okay, it may not be a straight line from left to right. It may be going through thousands of collisions, but it's generally making it way from the left to right. That's still fine. That's still called diffusion. Okay, diffusion also follows Graham's law of diffusion. So this law of diffusion and fusion are very similar. So rate of diffusion also is inversely proportional to the square root of molar mass. If you look at this mass expression, you may feel like, okay, the rate of diffusion and the rate of effusion, they probably are the same because the expressions are the same. But actually, the diffusion rate are much smaller than the effusion rate. Okay, when we have this proportion, and when we take this proportion away, we need to put a constant here, right? So those constants for diffusion and effusion are different. So diffusion rates are much smaller than effusion rates. If we kind of understand this, you can imagine the Black Friday, okay, when the doors open, everyone's rushed out, right? So this is effusion. So that speed is very quick. However, if we are just under a regular day, we just walk through a hallway of, a mall, whatever, so the speed is relatively slower. So that's the diffusion. Diffusion rate is slower than the effusion. For these two concepts, you are expected to know the rate, the proportion of the two rates, diffusion or effusion rates versus its molar mass. Then we can solve a problem about timing. Let's take a look at one example about diffusion and diffusion problem. At a given pressure and temperature, it takes 4.85 minutes for a 1.5 liter sample of helium to effuse through a membrane. How long does it take for 1.5 liter of fluorine gas to effuse under the same conditions? Okay, for this problem, it gives you two gases and tells you that it's diffused through a membrane. It gives you time for one gas and asks you the time for another gas to diffuse. So since it has two gases, we need to use the equation 5.14. The rate A over rate B equals to the square root of molecular mass of B over molecular mass of A. So we first plug in the numbers and see what we have. So rate of effusion of helium over rate of effusion of fluorine, plug in the numbers, should equals to 3.0822. What does it mean is that helium effuses 3.822 times quicker than fluorine. Okay, the rate is larger, it effuses quicker. That also means, under the same condition, the effuse time for fluorine, the diffusing of fluorine is slower, so it takes longer, right? So effusing time for fluorine is 3.0822 times longer than that for helium. Okay, since it's 3.0822 times longer, we use the time that helium takes to effuse through a membrane, 4.85 times 3.0822, and got the value of 14.9 minutes. That's the time fluorine, the same amount of fluorine takes to diffuse under the same condition. Okay, this is the end of this video. I'll see you next time.